Hello everyone, welcome to this Physics Paper 1 Night Before video. I'm Mr. Keyse and recording for TCASA Science. So to start off, we're going to have a look at P1, where we have the big statement: energy cannot be created or destroyed, only transferred from one store to another. That's a really big statement there, which is this one here. Now, stores. We have a handful of stores and a handful of transfers. First of all, we've got chemical, kinetic, gravitational, elastic, thermal, magnetic, electrostatic, and nuclear. Those are the stores that we need to look at. We've also got some transfers. We're looking at mechanical, so when you lift something up, when you move something, that is mechanical. Electrical, which is probably the one that we're most familiar with, using electricity to transfer energy from, say, a battery to a light bulb. We've got heating, and we've also got radiation. We used to call this sound and light, but we've actually dropped that whole idea because we can bundle it all into one thing. It's related to waves, which we'll have a look at in paper 2. There's a handful of equations here, where we've got work done is equal to force times distance, gravitational potential energy is equal to mass times gravitational field strength multiplied by height. Gravitational potential energy is also equal to weight multiplied by height. More on that in paper 2. We've got kinetic energy is equal to half multiplied by the mass of the object multiplied by its velocity squared. Notice it's the velocity squared, not the whole thing. That's a common mistake made by many students. We've got also power is also equal to the energy transferred, also known as the work done, divided by the time. It's the amount of energy that goes from one place to another in a set period of time. We've also got efficiency there, where we've got useful out divided by total in. Now, you'll see it in textbooks written down as useful energy out divided by total energy in. You may even see it written down as useful power out divided by total power in. It doesn't actually matter what we're talking about there. We've got energy and energy, or power and power. We could even talk about it in terms of useful sharks if we really wanted to, but that's a bit silly. Basically, mathematically speaking, the energy on the top line and the energy on the bottom line cancel each other out anyway. So, transfers. We have on the left-hand side here, we've got a chemical store, okay? And we can transfer that energy from the chemical store to the thermal store through the process of heating. This is just an example. It can be written down as an equation, which I know we all love equations, so many of them. But it's relatively straightforward. Now you'll notice that in this example, all of the chemical energy went to the thermal store. Now, a couple of key points here. Work done equal to energy transferred. Sometimes energy is lost to the surroundings. It's not destroyed, it's just not useful. Also, you may see in the exam something called a closed system. This is where no energy transfers take place out of or into the stores of that system. That's just something you need to know. You could think of the universe as a closed system. The energy that we had at the beginning is the same as the energy at the end. It's very rare in science to actually see a closed system, but in the exams they will probably talk about it in terms of a closed system just to make it easier to understand. We've also got a weight being the same as mass multiplied by gravitational field strength. More on that later on in paper 2 stuff. You'll also note that efficiency can never be above 100%. Okay, so if you've got the numbers, if you've got an efficiency that's greater than 100% from calculations, usually what we're seeing there is an error where you've got the total and the useful upside down. So if you flip the numbers, then you should get the right answer. Sometimes they can be quite sneaky in the exam, and what they can do is ask you to calculate using the useful out divided by the total in, and they'll give you numbers that will give you a percentage greater than 100. The next question, what you'll find, will be something along the lines of, what's wrong with this number? And what they're expecting you to say then is the efficiency can't be above 100%. The next thing we're going to look at quickly, we are going to have a look at this example here of a bungee jump. It's a favorite exam question. So we've got this little dude up here about to jump. At the moment, his gravitational potential energy is at a maximum. So when this guy then decides to jump, he's falling, his GPE is decreasing. His kinetic energy is increasing. Okay, because he's increasing, he's accelerating, he's moving downwards. Now you'll notice that at this point, the elastic band, the bungee cord, is still a little bit slack. It's kind of coiled up, it's not fully stretched yet. At this point here, just before it starts to stretch, you will notice that the kinetic energy is at a maximum. Okay, what we're then going to be doing is going to be losing some energy from gravitational potential energy and the kinetic store into stretching that elastic band. So here we go. The GP is still decreasing, kinetic energy is now decreasing, and our elastic potential energy is increasing. When the bungee jumper reaches the bottom of the bungee jump, the elastic potential energy is now at a maximum. This is at that instantaneous point where they're just at the bottom. They haven't bounced back up yet. They are at that moment in time clinging on for dear life in this particular example, looking about his fingertips. Anyways, going back up, GPE starts to increase, kinetic energy also increases because they start accelerating upwards, but the elastic potential energy starts to decrease. At the midpoint again, kinetic energy is at maximum. Now we've lost all of the elastic potential energy. Still carrying on upwards because we're still moving, we still have this kinetic energy going upwards. The kinetic energy starts being lost, turning into gravitational potential energy. Now you'll notice here, the bungee jumper never returns to the original place. So some of the energy has been lost to the surroundings. Now, that energy lost to the surroundings, heating up the elastic band, work against air resistance, that sort of thing. It's nothing to do with them screaming on the way down or anything like that. I know I had one student a few years ago talk about the bungee jumper might have eaten a sandwich on the way down or something along those sorts of lines. Rather ridiculous things. Ignore that. This is just looking at these simple snapshots that I've just demonstrated now. So that summarizes P1, conservation and dissipation of energy. Very, very, very quick crash course. What we'll look at now is P2, energy transfers by heating. So conduction, first of all. If we have, like we can see on the left-hand side, a solid, a metal, for example, metal ions all arranged in this regular shape, a lattice, a crystalline structure, everything regular. If we apply a heat source to that bottom left-hand atom, what we can then see is that that atom's energy store will increase. It will start to then vibrate. Okay, it'll start to move around a lot more. Its kinetic energy has increased. Now, as that heat source is still there, what's happening? That kinetic energy is being passed on to the other atoms next to it. Okay, so they have now got some additional kinetic energy. They bump into the next ones, and into the next ones, and into the last ones. We can call this lattice vibration. Okay, so it's called conduction through lattice vibration, and also you get movement of the delocalized electrons in a metal, for example. Okay, now there are required practicals with this one. We have materials as insulators. Different materials can be used to insulate identical beakers of hot water. Okay, so you could use, for example, here we could have one that's uncovered, and one that's covered in aluminium, cardboard, and styrofoam. The material that allows the water temperature to decrease the most in a set amount of time is the least insulating. Our independent variable here will be the material that we use, and our dependent will be the temperature change. Controls, we'd keep the same beaker type, the same volume of hot water, the time that we leave it to cool for, and the temperature at the start. That would be an ideal situation. The second one is the specific heat capacity required practical. we can look at it in terms of solids and in terms of liquids. So solids, we've got a thermometer placed into the block of material, like we see on the right-hand side here, and that's to measure the temperature change. The heater is connected to a joule meter and power supply. That's placed into the block of material as well. The mass of the block is measured using a mass balance. In liquids, we'd empty the beaker's mass. No, sorry, we wouldn't empty the beaker's mass. We'd measure the empty beaker's mass, and that'd be measured using a mass balance. We'd pour liquid in and measure the mass of the beaker and the liquid. The difference between the beaker plus liquid and the empty beaker is the mass of the liquid. Thermometer and heater are added the same way as for solids. You can then use this equation here, specific heat capacity is equal to energy transferred divided by the mass multiplied by the temperature change. Simple terms, specific heat capacity is the amount of energy needed to raise 1 kilogram of a substance by 1 degree C. Now you'll see it in some textbooks written down as not just 1 degree C, it will be 1 Kelvin. That's a whole different scale. You don't have to worry too much about that for GCSEs. You don't need to memorize this particular equation, you'll be pleased to know. You just need to be able to use it. It's a case of putting the right numbers in the right places and then summarize to then put your workings in, rearrange it after you put your numbers in, get your answer out and write your units. P3, energy resources. This is very much like a geography question. We have to use it though because it's a big thing in physics. What we need to look at first of all is the generalized principles behind energy resources and how we actually get our electrical energy. So we actually follow this same principle. It hasn't changed for, well, since the dawn of the steam engine. Basically, we just heat up water. That turns to steam, it turns a turbine, turns a generator, and this generates electricity. Nothing much has changed since then. Now, first of all, we're going to talk about fossil fuels. These include coal, gas, and oil. These are burned to release chemical energy stores. Nothing else, just chemical energy stores. Okay? Disadvantage of this, we get carbon dioxide released, which leads to global warming, climate change, rising sea levels. It does not have any effect on the ozone layer. You may have heard of something called the ozone layer. Do not mention that when you're talking about fossil fuels. Nuclear power. Usually using uranium or plutonium. Sometimes we use thorium. It depends on the type of reactor. These do not release carbon dioxide. Okay, they are not contributing to global warming. All you need are very small amounts of the actual fuel to get a massive energy release. Okay, disadvantages of this though, the nuclear waste needs to be stored. The problem with it is that it's heavily radioactive. It's really not pleasant stuff. We've also got wave power. So this is the first of the renewables. These are renewables now, ones that will never run out. We use the motion of waves to generate electricity. Disadvantage of this, generators are needed to withstand storms and they are quite difficult to access. Okay, they're out in the ocean. You'd have to get a boat to get out there. So if it breaks down, you kind of have to, well, hope for calm weather. Wind. Movement of the air turns the blades of a turbine directly, which is why it jumps in at the turn of turbine section here, and it generates electricity. Disadvantages. Some people don't like them. I know that sounds like a rather pathetic reason, but some people find them very unattractive. Some people believe that the sound can cause certain illnesses. The less said about that, the better. It's complete and utter nonsense. The wind, though, however, does not always blow enough to turn them. You'll see some of them just standing still. They're not generating electricity when they're just standing still. We've got hydroelectric. That's collecting vast amounts of water in a reservoir, which can be used to generate electricity. So basically, you block off an entire valley, cause the river to back up, collect the rainwater, and have a turbine there. That you open the gate, the water rushes through, and the turbine then turns. The problem we have with this is that large areas are needed for the reservoir. Some towns have actually been flooded intentionally for this. If you ever visit Wales, you may see this particular sign here. It translates to Remember Drewerin, which is a Welsh village that was flooded quite some time ago to make way for a reservoir. It wasn't used to generate electricity, but it was used to store lots and lots of water to be pumped elsewhere. This is a big movement in South Wales at the moment, or across Wales, so you may see it if you ever pop across the border. Tidal. The movement in and out of the water in an area due to the tides can be used to generate large amounts of electricity. Problem with this, or an argument that lots of people make about this one, is that it can damage habitats. There was a big plan to have a tidal barrage running across the River Severn, so basically from Weston-super-Mare to the other side of the Bristol Channel, connecting up possibly to Newport or even to Cardiff. The Severn barrage would have generated vast amounts of electricity, as well as providing a road directly connecting the southwest to South Wales. Solar. We have got photovoltaic cells. They don't actually heat up water or anything like that. They convert sunlight directly into electricity. Solar heating cells, however, they convert sunlight into thermal store of the water. So then that heats up the water, possibly turning to steam, turning a turbine, turning a generator, etc. We've also got solar furnaces, which focus sunlight onto a water tank to, again, heat up the water, turn to steam, turn a turbine, turn a generator, generate electricity. Disadvantage of all three of these is that you need sunlight. So imagine a part of the day or time of day that this would not work. Imagine which time of day that might be. Perhaps when it gets a little bit darker, when we kind of need some more electricity. Solar are good, but we need some way of storing that energy. Have a look at pumped storage if you want to have an idea of what we could do there. That's pumped storage. Last one, geothermal. So deep holes are cut into the ground towards radioactive rocks, and we pump water in. That water is heated up by the radioactive rocks, which turns to steam, turns a turbine, turns a generator, generates electricity. I'd like to think you're seeing a little bit of a pattern here. Okay, electrical circuits. So, first of all, required practical, length of wire. If we increase the length of a piece of wire, this increases its electrical resistance. There's more material in the way, such as metal atoms, in the way of that current. Controls we need to think of here. Thickness of the wire, material of the wire. You may even say use the same power supply or other such things. Safety is a big thing here. It's one of the questions they asked in last year's paper. Switch off after measurements. Why? So it doesn't overheat. Use a low power supply so it doesn't overheat. Don't use short lengths of wire, less than 10 centimeters. Again, to stop it overheating. The problem with overheating, A, you can have small fires and also get burnt. Not pleasant, as some of year 11 already know. Required practical, the second one here. We have got IV characteristics. First one, resistor. This is called an ohmic conductor because it obeys Ohm's law, V equals IR. We've also, there it is as well as a different equation, current is equal to potential difference over resistance. It's the same equation, just slightly rearranged. Filament lamp. You'll notice here that the resistance, or the flow of the current decreases, so resistance increases, as the temperature of the filament increases. The more energy that goes into it, the hotter it gets. Now, the problem we have with that is the fact that the more energy the filament gets, the more the metal atoms inside it will vibrate. And this causes an increase in resistance. It's harder for the current to get from one side to the other, which is why it has this very unusual shape. The last one is a diode. Most of them are now semiconductors, and they allow current to flow in one direction only. Current only flows in this direction when there's enough energy. You could think of it as that little dude that I've shown you before, flinging things from one side to the other. Work needs to be done to get the charge from one side to the other. You need to have some energy going into it. So talking about charge, charge flow is equal to current multiplied by time. So series circuit, as you'll see here, it's a single loop. You could have many components. You could have millions of components. You could just have one component in a series circuit loop. Current stays the same throughout the loop. Okay, it can't go anywhere else. It is stuck in that loop. However, potential difference will split across the components. If they're equal components, as in they have equal resistance, the potential difference will be split equally across them. The larger the resistance, the greater the potential difference needed across it. And the last one, parallel circuits. So you can see here we've got two loops, really, where we've got that first bulb in the top bulb in the first loop, and the second bulb, the one in the bottom, in another loop. You'll see that where the two bulbs attach to the main wires, we can call that a junction or a branch. Current splits at every junction or branch. Potential difference stays the same across each branch. If we're looking at resistors in series, total resistance is equal to the sum of all resistors in the series loop. Resistors in parallel, the total resistance is less than the resistor with the least resistance. And this little diagram here just shows an electric field around a positive charge. So note that the arrowheads point in the direction another positive charge would be pushed if brought close to this charge. Remember, two positive charges would repel each other, so they'd push apart. If you held one of them there and brought another one towards it, the force would be on the one that you bring towards it is in the direction of one of those arrows. P5, electricity in the home. First of all, we need to have a look at the safety features of British plugs. So here's a British plug. You hopefully have seen one of these and have actually taken one apart and put it back together. It's got an earth pin and wire. The longer earth pin is to activate socket shutters. There's a plastic band around the neutral and live pins. There's a fuse which will break when there's too much current going through. A thick, hard plastic casing so it doesn't melt, and also to insulate against the electricity. There's also a cable grip to make sure that the cable is secure in the plug. Now you'll notice here the neutral is the blue wire, the live is the brown wire, and the yellow-green one is the earth wire. The socket as well also has some safety features. They've got a thick, hard plastic casing. Sometimes they look like they're metal, but if you look closely around the pins, around the sockets themselves, where the pins go into, there's thick, hard plastic. There's also a shutter on there, on the live and the neutral sockets, that are only openable by a plug being inserted. And the earth socket is connected to the ground by wire, literally to the ground outside. So UK mains electricity has a potential difference of about 230 volts. This is on average, or the root mean square, don't worry about that. It's just the average in the home, and that's plus or minus 10 volts. So you'll see on some plugs that they're rated between 220 and 240 volts. On average, it's 230. Frequency of UK mains electricity is 50 hertz. That's important because in other parts of the world it actually runs at 60 hertz, so you will end up with a flickering effect sometimes if you try to plug in an appliance that's not designed for it. Most of them in the UK, most of them in the world now are designed to run at 50 and 60 hertz, and at a range of potential differences, mainly because we're in a global economy where we like to be able to take our appliances to other parts of the world, and also big companies like to sell them to other parts of the world. The next thing we look at is quickly the national grid. This is the national grid. We've got a power station on the left. We can see a step-up transformer. So the step-up transformer increases potential difference from about 4,000 volts at the power station to 120, 130, or even higher than that. The reason why we increase the potential difference is so that we have a lower current. This means that we have less heating of the wires over long distances, and this makes it more efficient to transfer electricity or transfer energy from the power station to your homes. If we're heating up the wires, then we're just losing that energy to the surroundings. This is just trying to minimize that heat energy being lost to the surroundings, making sure everything is transferred as electrical energy. We then have a step-down transformer, which decreases the potential difference to make it more compatible with homes. So your regular house is 230 volts. You wouldn't want to plug your mobile phone into that directly. So again, you will have a step-down transformer again in the plug or the power adapter for your mobile phone. That will drop it from 230 to 5. You'll notice their light industry has 11 kilovolts, so it's 11,000 volts, and heavy industry requires something around 33,000 volts. There's a couple of equations here, mostly around power. So again, revising from P1, power equals energy transferred over time. The same power is also equal to the current multiplied by potential difference. The same power again is also equal to the current squared multiplied by the resistance of the circuit. And again, efficiency is equal to useful out divided by total in multiplied by 100. Okay, P6, molecules and matter. This here, just a triangle showing you all of the different changes of state. So solids can go to a gas through something called sublimation. It'll go from gas back to solid through deposition. Liquid to gas is called evaporation. Gas to liquid is condensation. Solid to liquid, melting. Liquid to solid is called freezing. In a solid, as you should be aware, we've covered it many times, solids are tightly packed together. All of the particles are touching each other, okay? In liquids, the particles are still touching each other. So if you're asked to draw this diagram, you need to make sure that the particles are still touching. If they are separated, it's now a gas, okay? But in liquids, even though they're touching, they're still able to move freely. Gases, particles are not touching, freely able to move. If you're given a box for a gas, you could draw 3 circles scattered across the whole thing, and they don't have to touch. So there's a required practical. Density. We're going to look at regular solids first of all. So a regular solid is like your cuboid or your cylinder. Cuboid like a box or a block of metal or a block of wood or something like that. You measure the mass of the object using a mass balance, and you can calculate the volume using length times breadth times height. That's for cuboids, or for cylinders, it's pi r squared multiplied by height. Now you'll notice pi r squared is the cross-sectional area of the end of the cylinder, and then you multiply that by the height to get the volume. Irregular solids, mass of the object measured using a mass balance. You could place object into a full displacement can, also known as a eureka can. So you fill that up with water until it starts pouring out, let it stop running out, and then when you place the object in, water will come out of that spout. That displaced volume needs to be measured with a measuring cylinder. Whatever that displaced volume is, that is the volume of the object. Almost like magic or physics. In physics, magic is the same thing. Liquids, you measure the volume of the liquid using a measuring cylinder. Again, this is similar to the specific heat capacity one, where you have an empty beaker, you measure the mass using a mass balance, you pour the liquid in, measure the mass of the beaker and the liquid. The difference is the mass of the liquid. One thing we're missing from here is the equation. Density is equal to mass over volume. Now, specific latent heat. Latent heat of fusion, energy needed to change the state of 1 kilogram of substance from solid to liquid at its melting point. That's given this equation here. Specific latent heat of fusion equals energy over mass. Latent heat of vaporization. These are just fancy terms. Don't worry too much about them. This is the energy needed to change the state of 1 kilogram of a substance from liquid to gas at its boiling point. Again, specific latent of vaporization, energy over mass. Internal energy. This is a strange concept for a lot of us. It's the energy stored by particles of a substance due to their individual motion and position. It's simply the kinetic energy of the particles as well as their potential energy due to the position within the object. Gas pressure and temperature. Increased temperature of the gas, the particles have more kinetic energy. This means they're more likely to collide with the walls of the container and therefore have a bigger force. Larger force over the same area gives us a larger pressure. This one here is for the separate scientists, so this is for the GCSE science or the GCSE physics students only. Boyle's law. For a fixed mass of gas at constant temperature, pressure multiplied by volume is a constant. So if we increase the pressure, the volume must decrease, because that constant must say a constant. And just to round off the last bit of paper, we're going to look at radioactivity. So first of all, safety features. If you're ever asked a question on radiation safety, that can be summarized using the following. We've got distance from the source. The further away you are, the safer you are. Time of exposure. The less you're exposed to it, the better. Shielding. The more you have in front of you, the better. Sometimes you may have to be very, very close to a source, so you'll make sure your time of exposure is low and you've got lots of shielding. Sometimes you actually can't have too much shielding, so you'll increase your distance from the source and decrease your time of exposure. And sometimes you need to hang around a radioactive source for a long period of time, so you're better off looking at increasing your distance and increasing your shielding, just for safety. It's all about balancing these three things. So use that idea if you're asked a question on radiation safety. This is how you could structure it, talking about the distance from source, time of exposure, and shielding, giving examples of each. We then have the different types of radiation. So we've got alpha, beta, and gamma. So an alpha particle, it's 2 protons, 2 neutrons, the same as a helium nucleus. Not a helium atom, a helium nucleus. There's no electrons around this one. It has the symbol alpha, the Greek letter alpha, which looks like an A. I wonder where we get the letter A from in the first place, and the word alphabet. Charge, +2. It's 2 protons, +2. It is stopped by paper. It can also be stopped by about 5 centimeters of air. Beta particles, these are electrons fired out of the nucleus, not from the outer shells, from the nucleus. This is when a neutron turns into a proton and an electron. There's some other particle physics stuff there you don't need to worry about. It's given the symbol beta, the Greek letter beta, and it's given a -1 charge. It is stopped by about 5 mils of aluminium. Gamma, electromagnetic wave. The nucleus itself does a little bit of a rearrangement, gives a bit of a shake, and gives out this electromagnetic wave. Or even the electrons themselves can rearrange themselves after everything has fired out. It's given the Greek letter gamma, sometimes drawn as a Y, like you can see here. It's actually more like a fish doing a nosedive. Okay, it has no charge and it's stopped for the purpose of GCSEs by lead. We also have the different models of the atom. So this one here is the first ever one. Ancient Greece came up with this, the ancient Greeks. Basically, it's an indivisible object. The idea of the word atom comes from atomos, meaning indivisible. This is further reinforced by Dalton's work back whenever. And it was called the billiard ball model because when you're thinking of it in a three-dimensional sense, it's like a billiard ball or a snooker ball, tennis ball, any form of ball, something that can't be easily broken apart. This was disproven by Thomson with the Plum pudding model. So we've got this positive pudding with negative electron plums around the outside and on the inside, scattered all the way through it. They had really imaginative puddings at the time. Basically, this is a very bready thing with fruit scattered through it. Think of a really cheap Christmas pudding. We then had Rutherford with the alpha particle scattering experiment. So firing alpha particles through some gold foil. Some of them went through, some of them bounced back, suggesting that the nucleus existed, and that is where all of the mass of the atom, or the vast majority of the mass of the atom, is held, with these electrons flying around in these orbits like little planets. That was further then reinforced by Niels Bohr, following on from Rutherford's work, giving us this structure here. This is the Bohr model, B-O-H-R, where we have discovered the neutron at this point, and that the electrons live in shells orbiting the central nucleus. This isn't the final model of the atom. There's much more complicated ones, but actually for the purpose of GCSE, for A-level, and even for degree level, this is quite a useful model. Each one of these models actually is quite useful. It just gives you an idea of the structures at the time. So we're going to have a look at activity. So activity is the number of decays or disintegrations per second, and this idea of half-life. This is the time it takes for the activity or amount of undecayed atoms to fall by half. So this is a graph of activity against time. You'll notice I haven't put units on here because the units could be anything. We could have activity in decays per second, decays per minute, decays per hour, decays per day, decays per decade, etc. Time could be in seconds, minutes, hours, whatever. The units are unimportant in this one. You might be given a graph that looks a little bit like this. Now, you will have to try to calculate the half-life using this graph. Now, you know it's not a perfect curve. That's because in reality, radiation is a random event. Therefore, you're not going to get perfect results every single time. So you may have a bit of a wibble on the graph. Don't worry if there's a wibble on the graph. Just still follow the same procedure. Now you'll notice that we start off at 20,000 for the activity. Now to work out the half-life, we need to think about the time it takes for the activity or the amount to drop by half. Well, half of 20,000 is 10,000. So using this graph, we scroll across from the y-axis at 10,000, there we go, and we draw a line, a horizontal line, to the graph line itself. Then we draw a line down from that line that we've just drawn vertically to the x-axis. I'm going to call this one x. Okay, so x, as we can see here, is equal to 2, whatever the units are, 2 hours, 2 days, whatever. So that is our first half-life. Now we can't just rely on 1 because, as you can see here, the graph has a bit of a wibble. We have to do more than 1. So after we've drawn those lines there, we then need to pick some other numbers that are actually useful. So let's pick 16,000. So we go from 16,000, and half of that is 8,000. So back to 16,000, we draw across, we draw down to the x-axis, and we do the same for 8,000 and down again. And the distance across the x-axis, or the time across the x-axis, is now our next half-life. I'm going to call that y. And if we were to measure that, we could even use a ruler if we really wanted to. Y, you'll probably notice, is exactly the same as what we had for x. It is 2. This is just a happy coincidence. Now, let's get rid of that one there for the time being, so we're not confusing things. We're going to have a look at 8,000, and we're going to go to 4,000 this time. So we're going across, and we go down, and again, you'll notice, we're going to label this one Z, it's equal to 2. We now need to take the mean. As you'll see in the bottom right-hand corner, taking the mean means adding those three up, x, y, and z, and then dividing by the number of half-lives we've taken. Now, if we'd taken 4, we'd be dividing by 4. If we'd done 5, divide by 5. In this case, just for ease of use, we're dividing by 3. So 2 plus 2 plus 2 gives us 6, divided by 3, and that gives us 2. So the half-life is 2. Separate scientists, you need to look at fission as well. So neutron hits a large uranium atom, or plutonium, or whatever, causing it to split into 2 smaller daughter nuclei. This releases some energy and 2 to 3 neutrons, which then go on to hit more uranium nuclei. We call this a chain reaction. Okay, we go from 1 to 3 to 9 to 27, etc. It keeps building up and building up and building up, unless there's some way of controlling it, such as using a control rod. That tends to absorb neutrons, stop them from hitting uranium nuclei. If that didn't happen, we'd end up having a meltdown or even a nuclear explosion. Nuclear bombs run through this process very, very rapidly with complete lack of control. Another thing for the separate scientist is nuclear fusion. This is when we have two smaller nuclei, such as hydrogen and hydrogen, or two isotopes, deuterium and tritium, or tritium, however you want to call it, or even talking about hydrogen helium or deuterium and helium. These join together to form one larger nucleus, releasing energy. No fusion power station yet exists, but experiments are running. The running joke at the moment is that fusion is 10 to 15, maybe 20 years away. It's been that way since the 1980s. So, yeah. So thank you very much, everyone, for listening. I would wish you all the best for tomorrow. Well, actually, I do wish you all the best for tomorrow. I'm not wishing you luck because you don't need luck. You've been putting in some fantastic work, and I'm sure you'll be amazing. See you after it. Take it easy.